So we'll start with lecture number 12. And today you are also turning in the first homework. I've gotten 14 so far, and I'm not sure the other campus can send this by email to me, possibly. That's the most practical. So today we'll talk more about offshore systems. The last time we had the first lecture a little bit about the background in terms of what the trends are and what the energy needs are, and we started a little bit about offshore platforms. We talked about fixed platforms, and today we'll cover quite a few other types of offshore systems. So the last time, remember, we talked about the fixed platforms of two types. We talked about the jacket structures, which are steel structures made of tubular members. And we talked about one that's not shown on this slide, which is the gravity-based structures. Those are platforms that are kept in place by their own weight and normally made completely or partly by reinforced concrete. So today we'll get into quite a few other systems, like the tension leg platform, and we'll talk about semi-submersibles. We'll talk about a little bit about deep floaters. We'll talk about FPSO, floating production storage and offloading. And what we are seeing now is that there's kind of an emergence between offshore technology and, let's say, ship type technology. We are seeing these coming more and more together. And in one way that's good, isn't it? But also we have to be aware of that the offshore oil and gas regime is quite more strict when it comes to design than the shipping side of it. So quite often the requirements for a ship that's being used in an offshore context will be, let's say, more strict, more severe requirements than for a typical ship application. One of the types we will talk a little bit about is compliant tower. And there's one that was built by Chevron in the Gulf of Mexico called the Petronas Tower. And there's also something called Petronas Tower. Do you know that? Petronas is the oil company in Malaysia, right? They also build towers, but on land. And as a matter of fact, this structure is about the same height as the Petronas towers. So I guess it's a coincidence that this is called Petronas and the other one is called Petronas. But this type of, as you can see, it is a tubular member. All these crisscross space frame structures, we have all these complicated components, but in this case it's repetitive, right? I'm sure there are some variations in thickness, but in principle you see the same structure going all the way down, and then you have a strengthening and piling system, because this would obviously not be stable, would it? If you think about the wave loads and currents up here, if we didn't really attach it, almost like with hammer and nails to the seafloor, which is done by these piles, and they are hammered into the seafloor. So that's the way it becomes stable. But of course, since this is so large now, you see here, mud line to water line 534.6 meters from here and up there, and to the very top up to there 640 meters. So piling is certainly a requirement. It's quite flexible, but it may not be more flexible than other types of platforms which are floating. But obviously there's a limit to how much weight you can carry, and in this case you see that deck structure with all the processing. I'm not sure what the weight is, but if I'm to guess, I would say 20,000-30,000 tons. So there's no additional possibilities for storage. And of course, this is difficult to install. Imagine you coming with this floating, and then you have to upright it and get it into the right position, and then you have to do the piling, and then you have to put this deck on top. So it's a serious matter. Here you can see 2 ships carrying that deck structure. And of course, this kind of mating, as it's called, when you put the deck on top of the structure, can only be done when the weather is very good. So typically done in the summer, and whether there's a forecast of good weather for a long period of time. Then another type, and now we're getting towards floating platforms, but this is a floating fix. That is, it is movable. You see these deck structures, these are different types of these jack-up platforms. So don't mix the two up. We have a jacket platform, which is a steel frame. And then we have a jack-up platform. And that to jack up is to lift, right? That's, the expression jacking up. So you see these legs. They are, when you float the deck or the platform to location where you want to start drilling, then you start lowering these legs. And when they hit the seafloor, you start a system where you jack up the platform. There's a mechanical system whereby you can lift up the platform. It's not easy to see on these pictures. So typically you have to lift them up, the platform deck up till a distance which is suitable so that you don't get waves hitting the platform. In this particular case, you see the platform is lying at port, and of course this is just a test, right? So the advantage by this is that it can be moved, and it's rather flexible. The legs are very long, and it's adjustable to what sea depth you can use it. Well, certainly there's a limit, but you just jack this to be the right height in relation to the water surface. So you could see this platform could have gone to a deeper water depth than is the case. But can you imagine there are some disadvantages too here? Well, you can see this thing. If you go out at sea and you hit bad weather, right? And you have these high up in the air, and it can be a problem with dynamic motion. Another problem, which is probably even more severe, is that you tend, because you have a mechanical system, for raising up the deck, you tend to get fatigue in these connections. I'm not sure if such platforms have been built in Korea. No. But there are very many of them. I mean, it's and the advantage is that they are used mainly for drilling. To be there a few months to do the drilling, and then they go on to the next site. So we're getting more into the floating from the jack-up and tension leg systems of various types. Catenary mooring. These anchoring lines are called mooring lines when they are allowed to deform and they go out to the side like this, whereas when they are straight, we don't call them mooring lines any longer. We call them either tethers or tendons. Okay. Here is a type that's called taut mooring. It's sort of in between. So you have, this would be a TLP type configuration. And if it's rather with flexible mooring lines, that's what we call mooring line. This is what we call a tether. Or also a tendon. And then you have this taut mooring, which is something in between here, which is like this. And the advantage by the taut mooring is that it gives, you can see it gives you some extra stability in relation to the horizontal loading on the platform, right? You have this, but they have to be pre-stressed in order to function. So, of course, the platform has to be in the water somehow. But there is a problem with this taut lining, and that is typically these lines will have a point where they meet and the motion around this, what's called a pole, will be very little rigidity. Okay. So those are things one has to consider. Yeah. Just lots of pictures. You can look at them and see what you think. There are advantages and disadvantages by all designs. Typically, a design will have a limit with regard to how great water depths it will work, and of course also functional limits in terms of how much weight can it carry when it comes to the processing system on the deck. Can it carry 10,000, 20,000, 30,000 ton and so on? And then you have the capability of being able to store oil or not. So typically the floating platforms, most of them cannot store oil, but if you have a FPSO, then you can store oil. And we'll also talk a little bit about something they called Seven. It's a company in Norway that's developed this round cylindrical type buoy with a big storage. So that is possible. So drilling rigs, they are used in the early phase. What typically happens is that you do geoseismic measurements. You have these special ships which go back and forth, and do measurements of seismic signals that are sent from the ship and something behind the ship into the ground. And there it's reflected and sent back, and then there are sensors that pick up the reflected signals. On the basis of that, one can draw maps of the conditions underground. And today's technology is extremely advanced. So, location of these potentially valuable hydrocarbon resources underground, it's done with these seismic ships. So we'll get a little bit into that later on. But anyway, when a promising area has been identified, then the drilling rigs come there to start exploring, right? And sometimes that's when accidents happen. When a drilling rig, for instance, hits a high pressure gas pocket, and this gas wants to come out. And if it is able to come out, that's what's called a blowout. So if there's a uncontrolled stream of gas or oil or both, that's what's called a blowout. But anyway, these rigs are used for the drilling phase. So you have a semi-submersible, you have drilling ships, and you have also a drilling buoy, as you can see there. And there's a market, there's a worldwide market, and these rigs, they are towed or they go by own engine to various locations around. So you have drill ships, you have jackups, you have semi-submersibles that are used in the drilling operations. And you can see from these drafts whether there's a lot of business going on, or like here, and you have some years where the business is slow. And typically the prices for hiring one of those rigs goes up and down very much depending on the market. So it can be highly, highly profitable, but it also can be a loss. So a little bit more about semi-submersibles. And semi, that means half, right? And it's half submerged. It's almost look the same on top as under. But that was the first design. The H3 semi-submersible was developed in the 70s in Norway by the Aker Group. And nowadays there are many types of semi-submersibles. But what one would like is to have as little water line as possible, because we want minimum forces. But if we have very little water line area, then of course the platform becomes very unstable, because the stability is directly associated with how much area do you have in the water surface and how well spread out that area is. So there's always a conflict between having a large area and stability, right? So typically here you see you have buoyancy here underwater, and then you have these columns going up, and they have to have sufficient area to create the necessary stability. And of course, depending on how many of these legs you have, you may have or may not have a strong interaction with the ocean wave situation. So there are some with 8 legs, some with 6 legs, some with 4 legs. Isn't this picture remarkable? You see? I really have to wonder how can this be stable? But there are special ships. As you can see here, this is a special ship which is very wide, and it can, by ballasting, you can go deep, you can go underwater with it. So you can go under a platform, and you can go under, and then you deballast and you lift up. But the fact that this is stable, it's quite remarkable. So it's of course wide, but I don't think that is something that you could go into a storm with. And what we are seeing today is that these floating platforms are in one way becoming fewer than before, because typically in earlier times, when you had different wells, oil wells, you had to finish the oil pipes that come up, you have to finish at the platform. So that's why you have so many platforms in the Gulf of Mexico, because you have this old technology where you have to have, the wellhead, and where you can do the processing and stopping. You have to have that on a platform. But nowadays, there's technology where you actually, in one way, finish the wells on the seafloor, and you connect these wells that you have here and there, etc., with a pipeline, and then you finally bring it up to a platform, a floating platform in this case, where you do the processing, you do the separation of water, you do the separation between oil and gas, etc. So today we are seeing more and more subsea systems, and here you can see you can use a rather simple lightweight platform, because you have all these processing systems on the seafloor. So that is a real change in technology that has taken place over the last few years. So in one way, for platform builders, that is bad news, isn't it? We need fewer platforms than before. But of course, these are very, very advanced systems, so that is another business that one can get into. So I included this one just to make you understand that there are many types. If you're going to analyze a platform, there are many stages in an analysis. First, you make kind of a CAD drawing, which is often referred to as a concept model. You have a concept, you have an idea, you have a sketch of a platform systems, and then, with modern CAD, you can make a concept model. But to be able to analyze this, you have to do two things. You have to make a model for finding the loads on the platform, and that is typically done with CFD, computational fluid dynamics. In the old days, strip models, today panel models. You see these panels? They are surface descriptions of the platform, and with these hydrodynamic codes, programs, computer programs, you can find the forces and the hydrodynamic forces on a platform. Then you have another type of model, which is the structural model, right? If you have the panels and the forces on the panels, you can transfer that to a structural model, which is typically a finite element model, and you can find the structural forces and deformations and dynamic response of a platform. Of course, this becomes quite complicated if you have a platform which is moored and you have these forces that are changing with time and the platform starts moving, right? So then you have what's called fluid structure interaction, because the loads makes the platform move, and the motion of the platform again affects the fluid loads, right? So that's the fluid structure interaction. Some of you may be taking the course on fluid structure interaction. I'm not sure if you're getting into this type of situation, but this is very, very common. You know, you have to at least have heard about how one does this type of analysis by coupling fluids and structural models, and typically you can do a staggering, you know, you go from loads to structure, to back to loads to structure, in order to iterate and find a solution. Then this is what is called a global model. But then typically for a jacket structure or a semi-sub like this, we have severe concerns regarding fatigue, where we have stress concentrations. And in this business, stress concentrations are often referred to as hot spots. And in one way, you know, when you make a stress plot for a finite element model, you typically will use a color red, right, as the stress level goes up. So that fits in one way. You know, you have these red colored areas where you have stress concentrations and where you really have to be concerned with fatigue. Okay? So doing a very accurate, you need a very, very fine finite element model to find these concentrated stresses. So there are models on different levels: hydro, global, details, and also very many load cases. Some platforms have to be analyzed for 200 different load cases. Think about that. So I made this little sketch also to make you understand a little bit more about mooring. Because this is, of course, something you have to deal with ships and platforms and all sorts of marine operations. And there can be different types of mooring lines. It can be a rope, it can be a wire, high strength steel wire, it can be combination of steel and some fiber material, it can be a chain, steel chain, you know, links like this. And this is in one way a classic problem. If you have a rope, right, and you hang a rope, and what is the shape? That's what's called a catenary line or catenary geometry. It's a classical problem. So, for instance, in the old days, when they were going to design bridges that were resting on an arch, or they were going to design a church with a big arch, what they did was to take a rope, and they were hanging the rope, maybe having some extra loads on it if you were to have concentrated forces. And then they put some glue or some lack on the rope, and when it got hard, they removed the loads and inverted it, because it's a perfect force line for carrying loads. So one thing is going like this, but if you have the load the other way, you can build an arch also with the same type of equations. So what really matters here is you have a contact problem here, right? If this goes on, if you pull more here, and typically the boat will, or the platform will be pulled by either by it has to be held at least with a force. It can be a tugboat, or it can be a mooring line on the other side. So you have a horizontal force. If you increase the horizontal force, this will become straighter and it will lift up here. If you lower the force, it will go back. This will go backwards, and suddenly, this will, if it had some stiffness, it would actually break. Bending stiffness. And you have a mass per unit length, and you have a submerged mass per unit length, which is the weight on this. And the classical equation for a catenary is what you see here, hyperbolic functions. A first approximation of this kind of geometry is a parabola. And this is let's say, a rather smart way of expressing that geometric form. There's a parameter called A, and what you can see here is you have a grid of horizontal and vertical dimension in relation to the quantity A, which could be dimensionless, right? So if you have A equal a half, you go up 1/2, and you see it hits the one line at 1/2. If you have A equal let's see, 1. It starts at 1. I thought. Well, anyway, larger A makes a more shallow arch. But nowadays, you have these classical equations for the geometric shape. Nowadays, if you're going to analyze mooring of a, let's say, a floating platform, what we would do is a finite element analysis, right? We would divide this up in finite elements. And in a simple case where you don't have any stiffness in the line, you can actually use a bar or a truss formulation, where each element is a 3 degree of freedom system, right? So for an element, you have for each node 3 degrees of freedom, and for an element 6 degrees of freedom. It's very simple equations. You can write the stiffness matrix directly in the global coordinate system, and you can also deal with this in large deformation analysis very simply. And then, of course, here you can combine this with contact analysis, where you have nonlinear springs to model contact. So these springs would typically be that when you have contact between an element and the seafloor, you mobilize the forces in the spring when you get contact. But if you are away from the seafloor, then the stiffness is 0. So it's a nonlinear spring formulation. What else? You can also, if this is rigid, you can model, you can make this like one element. If it's a 2D, or if it's a 3D, you have maybe to have more elements. But you can model the floating structure with buoyancy springs. And why is that? Because it's a linear spring. When you push a platform, at least if it's vertical, if you push a platform down, then of course you have greater buoyancy. So in linear, not too large displacement, you can use linear buoyancy springs here. Okay, buoyancy. So one can make, of course, what one can do with some classical solutions, but it's better nowadays, I think, to do it numerically with a finite element, large displacement finite element model. And as I said, catenary, a cable type formulation, you have very, very simple elements. You can express those finite elements directly in the global coordinate system. And another thing, of course, computationally, the fact that all these elements are lying like this means that the bandwidth of your system of equations will be very, very narrow, efficient. So you can optimize and find the solution. Okay. There's also not only technology for mooring lines, but also for all this. If you have a floating platform, it will move, and you cannot have a stiff pipe connection, or what's referred to as a riser. A riser is where the oil and gas comes through, and you have flexible mooring, flexible risers, which are made of different types of steel and maybe fibers of various sorts and plastic of various sorts for these mooring lines. Riser lines. And this technology is very, very advanced technology. Difficult to analyze, actually. This is another example of a TLP, but it's built in concrete, the Hadron platform. And I have been involved in the analysis of this thing. It looks like a simple platform, but if you start looking at, these are two prefabricated concrete beams. The length, as far as I remember, is 180 meters long beam, height 12 meters. And so it's really enormous dimensions. But this is a tension leg, right? There's where the anchoring goes straight down, and these are pre-stressed. And you see there are 4 tethers, 4 of these cables per corner. And its design is such that if one break, the 3 remaining ones should be sufficient. You always have to think safety. So just a little bit more, 30,000 tons of pre-stressing. And I'll get a little bit into why this is. So the TLP principle, let's look at that. I made a sketch here on the right. So if you see here, a typical platform, the anchoring is vertical. And then, of course, you'll ask, if this is vertical, how about the stiffness in the horizontal direction where you have all the wave loads and currents loads? How is that possible? And these are vertical. Well, you have to do a geometric analysis where you look at finite displacements. And if you have a horizontal motion of u and the total length is L, then you have to look at the force balance at this platform. And in this case, all the tethers are, modeled here with one tether just to show the principle. So this is a floating platform. You have a buoyancy force, you have a weight of the platform, and normally, if you have a floating platform, the buoyancy is equal to the weight, right? For a ship, the buoyancy is equal to the weight. Well, in this case, the buoyancy is larger than the weight. And of course, it's kept down, pushed into the water by this anchoring line where you have a tension force or tether force T, right? So that's what you see here. But if you look at the finite displacements here, you see that if you have a horizontal force and the restoring force, which typically will be equal to the applied force from the waves, then you take this T and the sinus of the force, which is U over L, right? That's sine to this angle. And normally you formulate that as T over L times U. So this is the stiffness. So the stiffness matrix or the stiffness coefficient is simply tension force divided by length. So you, of course, this stiffness gets smaller the longer the L is, right? So if it gets deeper and deeper, the stiffness in principle becomes smaller, which is not what we want. But then, of course, you can apply a sufficient tensioning by making sure that the buoyancy is significantly larger than the weight of the platform. Okay, you see that? Pardon me?
What is the summarize the weight
of the well, of course, it turns out if you have a big platform, there's a significant weight of the tethers themselves, right? So the T force you have up here is smaller than down here, because here you are carrying. It's easiest to understand that if you look at the force here, in the other end, you also have to carry the weight of the submerged tether line, right? Because it doesn't have any stiffness. It doesn't take any forces in axial direction. By the way, it's in tension. So the force up here is bigger than the force down there. And we have to make sure that the force at the bottom is larger than zero, because this will buckle, of course, if there is not tension in this tether line. And if you have a dynamic response where it goes into compression and then, of course, back into tension, it will snap, it will break. So this is a very, very serious design condition. So not only to look at the static conditions, but also dynamic when this platform is moving up and down and rotating, then we have to make sure that the force in the tether line is all the time in tension. So that's that type of technology. I would say, so if you have a platform that weighs, the weight of it is with a deck, let's say 50,000 tons, then the buoyancy has certainly to be at least 70 to 80,000 tons, because you need 20, 30,000 tons in pre-stressing to have sufficient force in the tethers. And what you can do is to do a reverse calculation. You can take a platform like this, compute the environmental loads, that is the waves and the current on the platform, and then you will have typically some restrictions as to how large offset you will allow. Maybe that's about 20 meters, right? So if you know the force, you know how much offset, then you can calculate actually the necessary tension force. So you do kind of a reverse analysis in order to see how much tension force you need. So normally this pre-stressing of the tethers is done by, well, two ways. It can be by pulling one-on-one tether and anchor it to the platform, hydraulically, or you can attach all the tethers and then you have to have ballast water and you deballast, and the deballastation pre-stresses these cables. So typical properties, it's mainly for drilling and production, not suitable for storage, because you have to have not only carry the loads of the platform, but you have to carry a significant pre-stressing force by buoyancy. Suitable for moderate depths. If you get down to 1,000 meters, of course, you get more offset. The platform will move more back and forth. But you also lose some of this pre-stressing I talked about due to the weight of the cables, their own weight. So the tensioning force will be severely reduced as you get towards the bottom, and that can give some problem with the tether going slack. So it's suitable for moderate depths, large offset, must not snap, and then there are some dynamic response problems that are quite severe, ringing and springing, and in association with that also feather fatigue. These cables or anchoring lines that are these tethers, they are very, very expensive. High strength steel normally. Lately they have been looking at using carbon fibers for these anchoring systems for TLPs. For instance, Conoco has been working with that quite a bit. Yeah. Okay, then we'll take a break here. Yeah.
Slide 18.
Slide 18?
Yeah.
Okay, we can go back.
Is this app free body diagram for general case?
This is the principle.
I think in general cases the tension load is vertical, but in this case it is like this.
Yes, but I was trying to explain to you. This is how it starts, right?
Yeah.
It's vertical.
I start from here.
It starts from there, and then we are looking at when it deforms, and then this stiffness. That's the whole point. Is that the stiffness is not there unless you it's associated with an offset. When the platform moves, you see that this secondary force system comes into action. So it's really a geometric stiffness is not something you see if you just do a normal model of a structure. It's a geometric stiffness.
Geometric stiff.
Yes, it's a geometric stiffness. It's K of geometric is tension force divided by length. So, in a normal model, it's not there. But because this is pre-stressed, and the only way to see that the stiffness is there is to see what happens when you give it the displacement.
So it means the tension is which is the in the is the
That's what provides the tension provides a horizontal component.
This the tension is the conductor like is the spring.
Yeah, you can say it's like a spring.
It can.
Yeah, this is like like that's right. It's like a horizontal spring here, as if you for this one have the spring here. That spring would be K. The stiffness would be Kg, which is T over L.
Okay.
So it's in one way kind of imaginary.
Yes.
Imaginary. Yeah, but it's there. It's geometric. It's geometric stiffness.
Okay, so if the tension rod is the big, this is the strong.
Yeah.
It is harder to go to other side.
Yes. The bigger T.
Yeah.
The smaller the.
Small.
Yeah.
Thank you.
Yes, because the U is, let's say, the horizontal hydrodynamic forces divided by the stiffness, right?
Thank you.
Okay.
내년에 입시자 분명히 먼저 연락을 해야 내년에 그게 지금 생각이 이론이 걔네들이 융합이지 융합 전형은 다른 거예요. 우리랑 전형이 달라. 아 진짜. 그러니까 걔네는 자기가 티오를 갖고 가는 거야. 근데 교수님한테 다른 사람들이 연락을 하는 거예요. 그럼 먼저 연락하는 거예요.
Let's see. Are we recording now? Yeah. Good. So I had a question about this geometric stiffness, and this is a stiffness that you normally would not see in, let's say, a typical linear structural model, but it is there regardless. Any member where you have a tension or a compression has a geometric stiffness. When you do buckling analysis, when a column is buckling, that's due to the forces you get when it deforms, right? So the critical load for a column is associated with the compression in the column and the geometric stiffness. And I guess most of you have done buckling analysis of columns and frames. This is exactly the corresponding thing, but this geometric stiffness is now a tension. It's not a compression, and the tensioning gives these horizontal components that you see as soon as you start deforming. So this picture to the right is just an illustration of how the force does arise when you give it a lateral displacement, right? It's there. You see that at once the component of the tension in the tether. So you could in fact introduce a horizontal spring where the geometric stiffness is the resulting tether force divided by the length L. That's the geometric stiffness in this simplified analysis. Okay? Okay, let's see if there are more interesting things to think about. And I just attached, this is a series of platform that has been developed by the company Technip. That's just an example, but here you see different types of deep floaters, spars as they are often referred to. And here you see an illustration. They have a load, stabilizing load down here, and then they have the buoyancy part here, and in between there's an open system of a space frame. So you have a steel structure in between. So you can do all sorts of things. Here you see an illustration of a deep spar type platform. And you see how they have attached the anchoring, the mooring lines here. And of course you should attach the mooring line such that when you have a horizontal force, this is the point that gives you best balance so the platform doesn't rotate, right? Because this will be the stiffest point in the horizontal direction. So having wind forces and wave forces here is balanced by the weight and the uprighting force or moment by this heavy weight at the very end. But I guess it's a little bit tricky to get that into location, because it will have to be transported horizontally, because there are not very many places where you have, for instance, 100 meters of water depth to transport, right? So you have to think about, if you make a design, how are you going to put it or transport it to the right location? And if this is 100 meters, for instance, you probably cannot build that near the shore unless you do it horizontally. Oh, function of the red lines? Oh, those, you see, for some of these platforms, let's go back. Here, you see it even better. See this? Have you seen chimneys like this? Big chimneys for factories? Well, the thing is, if you have a cylindrical body and you have a flow, airflow, and in this case, of course, a water flow, like current, what you will get is vortex shedding, right? Like this. And each vortex shedding, a vortex, this is a vortex, okay? Each situation now where you release these turbulences will give you a side force. That's what's called, in the transverse direction, that's called a lift force. And you see, if you have a large structure, rather slow current, you may introduce these shifting forces in the transverse direction up like this. And this is a real fluid structure interaction problem. So you want to avoid this, what is called vortex shedding. And how do you avoid it? You try to break, you want to break these turbulences, and you break them by having these spirals going around. You see, almost like a fin that goes around, and that breaks this vortex shedding. So it's to avoid this kind of resonance. And if you have a large structure, this is often referred to large eddy vorticity. Large eddy vorticity, which gives you some concern, typically if you have a cylindrical structure. So then you have fluid structure interaction. And I'm not sure is Professor Park teaching this?
How to attach the
Into the sea, I get into a little bit about mooring lines, how we can attach those. That's a good question. It's important, of course. Here you have the uprighting, right? Drill ships. Largest drill ship in the world built by Samsung. So it's called the Deepwater Millennium. And you know, this is one way of getting into the oil and gas business from the shipping side, right? Drilling ships, drilling storage. No, I'm sorry, oil storage looking like a ship. Of course, you can have drilling on FPSO as well. But you know, ships are good to have. So, floating production, storage, and offloading. They often look like a ship, but they can also look like a rather clumsy box type structure. And of course, in these days, we are interested also in doing more processing on these floating platforms, like liquefaction of natural gas. Okay? And then you have to cool down to minus 164 degrees centigrades. So here you see a LNG ship coming directly to this processing and liquefaction unit, which is at the gas site. So it has these conductors, these risers going into the processing system here to make the LNG. So the number of floating production and storage systems, and here you have, when you have a floating ship, or let's say a floating box, then you have the advantage of that you can have storage. Whereas with a TLP, if you anchor it like this, you'll see very soon that it's difficult to handle such great variation in cargo load. Okay, but number of units in the market, you see there are many FPSOs coming. And the TLP and the semi would typically be without storage. Spar could be a storage if it is of a particular type. Yeah, this is just where you see the markets for these. So floating, storage, offloading. You see in Malaysia quite a few. Africa. FPSO here in Brazil. And the two most interesting offshore areas at the moment are of Brazil and of West Africa. But it's deep water, both places very deep water. Yeah. Projects. I think if you are interested, you can look at it. And planned up to year 2012. And you see where the action is: West Africa, South America, that is off Brazil. And the old areas, not too much happening there, right? So this is a type. So some engineers in Norway, they thought they could combine a floater, like a spar type platform, with storage. And these have become extremely popular. Here you see this crazy thing of transporting this enormous structure on the ship. Huh? So there are quite a few of these that have been built. And those who came up with the idea and were able to develop it into a commercial technology, they have become very rich. Yeah, this is old, and this also, the first FPSO that was built as a FPSO was also a project in Norway. It sounds like I'm only talking about Norway here, but you know, very many of these new concepts have in fact come from Norway. Whereas in the US, where you had a more established oil and gas industry, they had their traditional solutions. So that goes back to 1986, the first FPSO. And typically what you see is that these are, you see, this is what's called a turret. That is a point where the ship can rotate. So a turret can be above the water, but it can also be under. And to do it under, you have to be able to pull it in and attach it. And there you not only have the anchoring, which typically would be some sort of mooring system, but you also have the flow lines, the pipelines coming up there. So everything can rotate. And of course, this is very important when it comes to severe weather with a storm, you know, big waves, lots of wind, and the ship, since it's attached either here in the front or down here also in the front, it will rotate and face the severe weather, right? And that is absolutely the best direction for a ship type structure. So this is something I've been trying to convince the people here in the mobile harbor, that when they make a B-type mobile harbor, it should rotate according to the weather. And then, of course, the docking and everything will become so much simpler when this mobile harbor or the FPSO is facing the weather. The technology is available for it.
Which one is more useful?
I think today we are seeing more and more this underwater. That, you know, it pulls in the anchoring, the mooring system, and the conductors, the pipelines under. But, you know, another solution would be to have a big buoy that and then you anchor the ship or the FPSO, whatever, to the buoy, and you can rotate around the buoy.
Is there a problem, kind of stress due to moon pool?
The moon pool, you know that expression, okay? Yes, of course, but you know, this is very sophisticated technology, and I think these systems are considered being quite robust now. So, for instance, shuttle tankers that come to get oil, you know, they can attach the flow lines, you know, from the storage under the shuttle tanker, or of course it can be a boom and pipes going over. But it's good technology now. Yeah, here you see this submerged turret system, right? So you see two types of lines. This one, this is a catenary, this is anchoring. Here you see anchoring with a big load at the end, right? And then you have these things that goes in the curl. They are not for anchoring. Those are flow lines. That's where the oil and gas comes in. And they are curved like this because they are not supposed to take any force, but they have to be flexible because the ship will move, horizontally as well as to some extent also vertically. So that's where you have these where you don't want the high tension. And at the same time you have also anchoring. Actually, I think maybe these are the anchors here, and these are the flow lines, right? So these are some subsea systems here, and you see all the tethers. It's not so very clear, but these are anchoring points of the mooring lines. And here you see a system where you have FPSO, storing oil, processing oil, and then you have a ship coming in. You see there is a bridge over here, and there you can connect the pipelines for filling up this ship with oil. So you are not dependent on having a pipeline going to shore with this kind of system. Very large FPSOs, enormous. Not exactly beautiful, huh? But functional. And barges, A little bit, I made this one about anchoring. You can have soil anchors and the traditional type of anchor that you have for a ship. And typically the anchor will have pieces that when you pull, it digs itself into the soil. Then you can have a very heavy chain, enormously heavy chain. And in offshore industry you can see chain elements that are like this, enormous. Of course you can have loads. You can have some very large loads and by friction keep things in place. But you see these loads that are lifted up, they help keeping the tension in the mooring line. You can have piles, as we saw for a compliant tower, but they can also be used for mooring. And then there's something called a suction anchor. What it is, it's like a cylinder with a cap on top. And you see when you pump out the water here, or maybe there's some air, but the air typically would be very compressed. But you pump out the water, you create the underpressure, and this is sucked into or it's pushed into the soil because of the pressure on the outside, right? So it's the water pressure that presses the suction anchor into the soil. So of course you may have almost any combination of these things. But typically at the end of a mooring line you would like to have some reserve, some extra strength in terms of some sort of anchor or extra heavy weight. Or maybe piling. Okay. Then there I mentioned the regime for something disappeared. Let's see. Do I go to this one? No. How do I get something that's hidden here? Can you show me? There's some secrets. Huh? Okay. Anyway, I'm not able to get it to show, but it's what is here is kind of a pyramid that illustrates the documentation, and I think you have it in your PDF version. Specifications, standards, recommended practices. These are different levels of documentation. There's also something called guidelines. And so there's a very strict regime for documentation of that structure is safe. But typically in offshore, the regime is different from the maritime business. You know, in shipping, we have classification rules that have to do with the structure and the integrity, the stability of the ship itself. And then there are other international rules that have to do with pollution, environmental performance, safety for crew, SOLAS, and so on. Right? In the offshore business, there are also regulatory bodies, you know, the directorates, petroleum directorates, for instance, that is overseeing that what is built on the continental shelf of the country is done in a safe way. But the main principle in offshore is that the owner, you know, the one who owns the platform, the operator, is totally responsible for the safety. So he cannot blame that, you know, there are some rules that are not good or whatever. The total responsibility is with the owner or the operator of the field. And typically there are several oil companies that go together to develop a field to distribute the risk. But you can go, for instance, to the homepage of DNV and you find all sorts of recommended practice, guidelines, and standards that apply. Supply ships. I mentioned supply ships before as an example of very valuable ships. And these small service vessels have a tremendous machinery on board because they are used, for instance, in some towing operations, in moving anchors, heavy weights, and they have to be at the field, you know, all the time. A big platform has to have an assisting supply ship. So regardless what the weather is like, you know, the supply vessel has to be out there. And I can tell you that, you know, this kind of job is a tough job because you have a small ship that moves a lot, you know, when it storms, and you have tremendous machinery, power on board that makes noise. So it's pretty tough. And of course you have dynamic positioning systems and all sorts of propeller system to maneuver the ship into both position and the right direction. And this is an example that it can go very wrong. And you can Google this if you want to. You can see also some animation of what happened to this rather new service vessel that was used to move anchors, heavy weights, because the platform was going to change position. And normally that is done with two service vessels at the same time. In this case, they tried to do it with one, and it didn't have enough power. And what happened was that there was such a heavy weight at the same time as there was a storm, and the result just so that line, of course, it has a guidance back here, but as soon as you also have kind of a geometric instability, because this is higher up, and it started pulling down the boat, and suddenly it went over like that, and some people lost their lives. So it's dangerous. Offshore business is dangerous. I mentioned geoseismic mapping, and this is done by a vessel that pulls some stringers, some long lines behind it. And what they do is to make explosions. In the old days they used dynamite. Nowadays one uses release of compressed air, and this is done very, very frequently. And some very sophisticated sensors that can record the reflected signals, and typically you get a reflection from the surface, and then you have different sedimentary layers in the base rock, and you can, from the type of signal that you get and a lot of experience, you can make a map of where you think the hydrocarbon reservoirs are. Extremely sophisticated technology. And of course, in the ground you get compressive waves, so-called P waves, but you also get shear waves and surface waves. But looking at P waves and S waves, and the shear waves go slower than the pressure waves. This kind of technology now is, you can make a 3D virtual reality mapping of what is down in the ground. Quite amazing. So this is another sector where many vessels, for instance, are built in Norway. Here you see this, you're pulling these lines behind the ship, stringers, and they can be up to 30 stringers. And of course they are made so that they will spread out. So when you go with your ship, you sweep an area, you go back, and then you go to the next. So you make a mapping, right? Very advanced technology. And you see this very wide rear part of the ship. That's because we want to have many of these stringer lines going out for absorbing the signals to get the widest possible picture. And this is what's called a ram form. Not very efficient hydrodynamically. A lot of resistance when you have a design like this, but serves the purpose for doing this kind of recording. So then I have a little bit of time, and I put together something that I can talk a little bit about now, but you should also start thinking about it. Maybe I'll give this as a homework for you. But I made this one. Design a 500,000 cubic meter oil storage in the ocean. And the following alternatives: floating on the surface, so it can be a box cylindrical tank, either with catenary mooring, anchoring, you know, this kind of behavior, right? Or TLP, is that possible? Or a tank ship, you know, FPSO, at least storage and offloading. And a single mooring line, multiple mooring lines. And then, because this is a problem that this department has been struggling with for CO2, storage in the middle of the water for the CO2 at 600 meters water depth, because that will give the right pressure for CO2 at 20 degrees or something. So is it possible with a floating tank? Let me make a drawing. So in the first case, you know, it's floating box that either have catenary mooring or TLP type of anchoring system, right? So this is A1, this is A2. And then the ship I don't have to describe. Then we have the submerged. Water here, and we have a tank. And of course, if you submerge it, you don't have to worry about wave forces and much less current forces, right? So this could be with catenary or TLP, right? Somehow, some anchoring. Okay. So this is C1, this is C2. So is that possible? 500,000 cubic meters. Density of the oil is 900 kilograms per cubic meter. Okay? So the thing is that the oil is floating inside here. So depending on how much oil you have in the storage, you know, the water level inside will be high up or lower down. Understand that? In reality, you'll have a bottom plate, but with some openings here. Otherwise, it will be a pressure tank, so that wouldn't work. Okay, and then finally, we put the whole thing on the seafloor. Right, and you have in here oil or water, depending on whether the tank is full or not. So that's on the ocean floor. Is that possible? And it says here it can be steel or concrete. So things you have to think about is, you know, the oil is lighter than water, right? And of course, you have to consider the tank being empty or full. That means the whole system changes weight. Maybe not in the way you think first when it comes to a submerged system. It's interesting. So let's put it this way, that this is something that you could start thinking about yourself. What are the technical problems associated with this? What solutions are possible and what are not possible? And it's not all that straightforward. Okay? Any questions?
So do we submit the report?
Not yet. I may. Well, I took a look at your first homework, and it looks good. You have been doing some good work. There's a lot of, you know, I'm trying to make problems that make you think. You know, I try to make problems where you can't go to a textbook and find the answer. You have to, you know, analyze the problem. You have to think about the principles of physics and mechanics in order to solve it. And I can formulate something in connection with this too, because I think it will be a good exercise. Other questions, comments? So on Wednesday we will have the last hour of offshore, and it will mainly be about accidents, because accidents have tremendous consequences. So it's always very, very important to be aware and analyze what can go wrong. And there are many, many examples of that things have gone terribly, terribly wrong. So that's enough for today. Good.